Welcome to this session. So, in this session we are going to discuss about transmission lines. So, before that just let us imagine a communication system. That in that communication system, what are the basic components we have? The basic components are it's obviously the transmitter as well as our receiver. So, whenever we are transmitting a signal from the transmitter, the receiver receives the signal through different mediums. Here what are the mediums we discussed in our wave propagation? It is a purely air. There is nothing in between our transmitter and receiver. But here in our transmission lines topic, we are going to discuss about the physical medium. So, what is a physical medium? A dedicated medium which is connected between it is clearly the transmitter as well as our receiver. That whenever the transmitter is transmitting the signal, it is only the intended receives the signal. That a physical medium in the form of whatever it may be, that may be a transmission line or a simple wire or a waveguide, that it will useful for transmitting the signal from a transmitter to a single receiver. So, here what we are doing is we are going to observe what are different characteristics of the transmission lines. So, depend upon different parameters and how to get the wave equations when a wave is transmitting in the transmission lines, and what are different parameters which are to be observed for a transmission line in this entire topic. That what we do is before that just we will observe what is the general scenario. So, where these transmission lines will be used and where the remaining waveguides or remaining physical medium will be used. Just here the main motto of using a transmission line is to get a distortionless or a lossless transmission at the high frequencies. The one and only point we are supposed to remember is at high frequencies. If you are using it low frequencies, it is no problem, whatever may be the medium, it is easily you can get the signal. That as an example, if you take the power transmission, is at low frequencies. That at 50 Hz you are transmitting a signal of 230 volts. That we are using a simple conductor like an aluminum wire or a copper wire. So, using that aluminum or copper wire, easily a low frequency, that is a 50 Hz signal can be transmitted from one place to another place without distortion. But if you are increasing the frequency, as we seen in our previous sessions, so the frequency increasing will gives you the attenuation. That the attenuation causes loss in the signal. So, the normal conductor medium is not at all suitable for high frequency, very high frequency and microwave frequencies. That is why what we do is we will try to go for another type of transmission medium. The transmission medium is transmission lines for high frequency and very high frequencies, and that may be waveguide for microwave frequencies. That at the high frequencies we are going to use these transmission lines. So, what is the basic difference between the low frequency waveguides or the transmission channel and the high frequency transmission channel? Clearly remember, there is no difference except in its structure. What we do is just we will use a twisted pair cable at the low frequency. That what we are using every day in our day to day life. That in our day to day life you may observe a twisted pair cable, that two cables will be twisted like this. That with that low frequency signal can be transmitted. But what is the structure when you are going to the high frequency or microwave frequencies? That we are going to discuss in this section. That a transmission lines is purely meant for a high frequency message transmission. Here we are not going to use any power transmission, just we will use a message that is in the form of electromagnetic wave. Then what is the basic structure of transmission line? Just observe here. Here what I am doing is I am taking two conductors. So, in our twisted pair cable also there are two conductors, there is no difference. Here also I am taking two conductors, and in between these two conductors I will place a dielectric medium. And when I am designing this one, I have to take utmost care, because here we are transmitting a high frequency signal, we are not transmitting any power signal here, we are transmitting a high frequency electromagnetic wave. So, what we have to do is just we have to embed an that is a dielectric medium in between these two conductors. This is the basic structure that what you can expect, and clearly observe that there is no twist here. Similarly, there may be another structure which may be like this. That these two are two conducting parallel plates. Between these two conducting parallel plates, once again I am embedding some dielectric medium. This is called as a planar line structure. This is called as a two wire line structure. This is a planar line structure. Between these two plates, some dielectric medium will be embedded. This structure is similar to your capacitor structure. The capacitor structure also same. And at the micro frequencies, this will be just modified as a micro strip line. That instead of taking the entire strip, we will take a small part of that strip. That will be useful for microwave frequencies. This is another structure for electromagnetic wave propagation. Similarly, another structure is there. This third structure is nothing but a wire above conducting plane. Let's say wire above conducting plane is our next structure. Like this, simply observe what I am taking. Just I am taking two conductors and in between them some dielectric medium will be there. Here also two conductors, between them some dielectric medium will be there. Here also two conductors, that is one wire and one conducting plane. Between these two, it's a simple a dielectric medium will be there. So in general, what you can say is a transmission line is a structure in which definitely two conductors will be there, and between those two conductors a dielectric medium will be embedded or sandwiched. Then only it will be useful for transmission of an electromagnetic wave. Later we will observe how it will be useful for electromagnetic wave and how to analyze that one. Now, how to analyze our transmission lines? Just we manufactured the transmission line, right? That after that one, how to analyze that one? For the analysis of transmission line, we have to take two different types of constants. They are divided as the primary constants of the transmission line and secondary constants of the transmission line. So before that, what we have to do is just we have to observe how to draw a transmission line. As we know, the structure is consisting of two conductors and between them some dielectric medium is there. But that is not at all suitable for analysis. So what we have to do is we have to convert that entire mechanical structure into electrical structure. That what we have to do is just we have to replace the conductor with equivalent components. We have to replace our dielectric with its equivalent components. Then only it is very easy for analysis. And once again remember, here we have two categories for the analysis. That is the wave propagation analysis, that is the wave analysis and circuit analysis. That E and H we will use for the wave analysis or field analysis, and V and I will use for circuit analysis. In our transmission line theory, the circuit analysis will use as in equations in a simplest way. That's what we do is just we will use this circuit analysis for analyzing our transmission line. So what are different parameters we are supposed to consider for a transmission line? Just clearly observe what I am doing. Just I will take the transmission line structure and I will try to give you or I will try to replace the components in the transmission line with its equivalent. So what are the structure or what are the components in our transmission line structure? A conductor. That this is one conductor and this is another conductor. Between these two a dielectric medium will be there. So don't think that these two are just two wires, just they may be conducting plates or they may be plates of some other shape, right? Just what I am doing is I am taking two conductors, between these two definitely some dielectric medium will be there. Now the conductor will be categorized with its characteristics like conductivity of the conductor, that is sigma c, permeability of the conductor mu c, permittivity of the conductor, that's epsilon c. Similarly, the characteristics of the dielectric medium will be characterized with its sigma d, that is conductivity of the dielectric medium, and permeability of the dielectric medium and permittivity of the dielectric medium. So what we do is initially we will select a appropriate material that we will choose. It's a perfect conductor for this one, that with low loss a perfect conductor will be useful here, and similarly a perfect dielectric may be used here for the construction of this one. Later how to go for the analysis? Just imagine this conductor will have some resistance. Every conductor in our universe will have some resistance. If there is no resistance, definitely this will be an ideal conductor, right? So what you have to do is you have to take the practical conductor and replace this conductor with the resistance existing to it. That what I am doing is I am taking the conductor, I am calculating the resistance. So instead of the conductor, I can place a resistor instead of that one, since it has some resistance. But this is not only sufficient. We have to take the inductance of this one also. As we know, every conductor can act as an inductor with little structure, right? Even though there is no loop structure, this will be acts as some inductor. That's why I will take inductor also to replace our conductor. So clearly our conductor can be replaced with the combination of a resistance and inductance. And what they are? Are they lumped elements or discrete elements? No, clearly remember they are distributed elements. Distributed means they will be uniformly distributed over the entire transmission line. That we are not supposed to place this resistance at a single location for the analysis. We are not supposed to place this inductor at a single location for the analysis. What we have to do is we have to uniformly distribute this structure throughout the conductor. So here and here what I have to do is I have to draw a series resistance inductance combination. So simply whenever I am trying to replace our conductor, I have to take a series resistance inductance combination. As these are distributed elements, they will be calculated per length. So here whenever we are observing this one, that is a resistance This is not clear pure resistance, this is resistance calculated per length, and the units are ohm per meter. Similarly, this is a distributed element. So, what you have to do is you have to calculate the inductance, how much we are observing per length of the transmission line. So, these two components will be useful for replacing our conductor. So, one problem is over. Then how to replace our dielectric medium? As I said, what we do is we will take an appropriate dielectric medium for this one. That a perfect dielectric medium is an ideal, it is suitable for that, but we don't get any perfect dielectric, so we will take the appropriate dielectric. Then how this dielectric medium will be replaced? With which electrical components this will be replaced? Just observe. In an ideal case, the conductivity of the dielectric medium must be always equals to 0. But in practical case, it is not at all equals to 0. So, what we have to do is you have to take that conductivity of the dielectric medium for the purpose of analysis. So, what I do is I will replace this dielectric medium with conductivity, that is represented with Z. Once again, this is a distributed element, this is not at all a lumped element. So, the units are mho per meter or Siemens per meter. And again, observe the structure of our transmission line. The structure of our transmission line resembles our capacitor structure. Here we have two conductors, in between them a dielectric medium will be there. This is similar to the capacitor structure. So, definitely some capacitance will be there. So, what you have to do is you have to take that capacitance also. Between these two, the capacitance may be represented here. That this capacitance also a distributed element, that units are farad per meter. So, just these four elements are sufficient or required to analyze our transmission line. That once again clearly remember, to analysis what we have to do is you have to replace the entire conductor with the series combination of resistance and inductance, and the entire dielectric medium will be replaced with the parallel combination of, that's why it is called as a shunt element, a parallel combination of conductance of the dielectric medium and capacitance in between these two conductors. That is why they are called as the primary constants. That the primary constants, whenever you are asked to write down about the primary constants, simply remember resistance, the resistance is measured at conductor, inductance which is measured or the observed for conductor, and conductance of the dielectric medium, that which is observed for clearly dielectric, don't go for the conductance of conductor, conductance of the dielectric medium, and the capacitance between two conductors we are observing. So, clearly remember, whenever we are trying to draw the equivalent circuit of our transmission line, just ignore the conductors, dielectrics, etc., etc. Just take these primary constants and arrange them as per your requirement. That you can arrange them like a pi order or L order or T shape. That what you have to do is, for the analysis purpose, you can take the required arrangement for a differential length of the transmission line. And clearly remember one more point, that as I am saying, it is measured per length, clearly all they are distributed, and don't replace the entire transmission line with single resistor, the entire transmission line with single inductor or capacitor. It is wrong. What you have to do is, whenever you are representing a complete length of the transmission line, write down a series combination of resistor, inductor, and a parallel combination of conductor as well as conductance as well as capacitance. Right? So, here clearly, if I want to draw the equivalent circuit of this one, this is the equivalent circuit of our transmission line. For a given differential length. Just what I am doing is I am taking a differential, a small length. For that, I can replace that one with R, L, G, C. So, this simple circuit is useful for us. It is nothing more than that. What we do is, now we will take this simple circuit and we will analyze this simple circuit for propagation of the wave or the propagation of the signal in our transmission line. And remember, need not to take this structure only, you can take T structure as I said, or you can take pi structure, or you can take L type structure. Whatever may be the structure, it's the equation may little bit vary. What we do is, we will take the convenient structure for us. So, clearly these four are called as, that is R, L, G, C are called as primary constants. Using these primary constants, we will go for the wave equations, and then we will go for secondary constants. Those secondary constants are most useful for analyzing the wave, how it is transmitting in the transmission line. That's why they are called as secondary constants. Here we have two secondary constants, they are called as propagation constant. It is represented with gamma. That already we gone through this gamma in our wave propagation. There also we have propagation constant. Here also we have propagation constant. That propagation constant is for the free space or the medium where the wave is transmitting. Here this propagation constant is for transmission line. Right? Similarly, Another constant is characteristic impedance Z0. There also we have characteristic impedance, that's we call that one as intrinsic impedance, right. Here this gamma and Z0, these two are described as the secondary constants for our transmission line. Now in this session what we do is just we will try to analyze the transmission line, we will try to get the wave equations for that one, and from those wave equations or the equations of this transmission line, we try to get the secondary constants also, that gamma and Z0 we will try to get. Just observe the structure of our transmission line. In this is resistance is ohm per meter, inductance is not ohm per meter, this is Henry per meter. The units of inductance which is distributed for our entire transmission line is Henry per meter. Please ignore the previous one, that we are supposed to take the inductance Henry per meter. Now what we do is we will observe what are different transmission line parameters, that is the primary constants for different types of lines. Here we observe different types of lines, that is a coaxial line, a two-wire line and a planar line. For those lines what are different parameters, primary constants were given. So don't go for any rigorous analysis and don't go for any derivations, just try to remember them, they may be useful. That the RLGC value for a coaxial line was given as 2 pi delta A, it's multiplied with 1 by A minus 1 by B, and the same resistance for a two-wire line is given as 1 by pi alpha delta A. It's like that different equations we have for RLGC of the coaxial lines. Just you go through the PPT so that if you practice them you can remember those equations easily. Now a very interesting point, that what is the relation between all these things, that we represented our transmission line with the combination of RLGC, but we have a unique relation between all these things, we need to remember them. Remember, it's the first point and the very important point is that it is a clearly distributed structure, that the entire RLGC are distributed over the transmission line, they are not at all lumped or discrete. So discrete or lumped means they will be placed at a single location, we are not placing them at a single location. For the throughout structure we are replacing them as instead of conductor as well as our dielectric. So clearly what you have to do is you have to remember that they are distributed elements. That's the first point, important point you are supposed to remember. And the second point, here we have two parameters, that is resistance and conductance. In general case what we think is the resistance is equals to the inverse of conductance, that what we write 1 by sigma or 1 by G, that what we write in general case. But here this equation is not applicable for our transmission lines, clearly remember that point. Why it is not applicable for our transmission lines? Here this resistance is observed for conductor, that what we are considering, that we are not observing for a single component, we are observing for the entire conductor in our structure. So this resistance is R is calculated for conductor and this G is observed for dielectric medium, this is not measured for conductor. So clearly through this one, so what you can say is R is not equals to 1 by Z here. Okay, this R is equals to 1 by Z is for general lines or general equation, but this R is measured for conductor, G is observed for dielectric medium. So these two are two different materials, that what we are considering. That's why this R is always not equals to 1 by Z in this case, in this particular case. And one more interesting fact is that you have to remember a simple relation, that we have a very interesting relation, that L multiplied with C, that is the distributed inductance multiplied with the capacitance, is equals to, don't go for any complex equations, just I will give you the simple form, L corresponds to mu, that L is directly related to mu, C corresponds to epsilon. So for observation what you do is just I gave one PPT earlier, take the equations of L and C from that PPT and multiply them. What you get is this equation, that L into C is equals to mu into epsilon, that what we get. So this is useful for remembering any of these two. If you remember C, already we learned how to derive C. So if you remember this C, easily you can observe L. So don't remember L, just you remember C, that's enough. So using this equation, easily you can get the L. And similarly we have one more relation, that is a very simple equation, G by C. Now easily you can say, so what is the ratio of G by C? So from this one, L corresponds to mu, C corresponds to epsilon. Here also G corresponds to sigma, capacitance corresponds to epsilon. So these two are two important equations which are useful for remembering the RLGC parameters of our transmission lines. So just what I do is I'll tell you a shortcut, that only remember this C. Here and here just you remember the C. If you remember C, you can observe G, you can observe L, and the resistance you have to remember. There is no other choice or alternative to this one. Just resistance, the complete equations of the resistance you can remember, and complete equations of the capacitance you can remember. If you remember these two, L and G, you can easily get from these relations, that is L into C is equals to mu into epsilon. So, G by C is equals to sigma by epsilon. So, these are 3 or 4 important points which are related to the properties of these parameters or the transmission lines. Okay, clearly. So, just remember them. Now, we will go for the analysis of our transmission line. What are the wave equations of our transmission line? So, what we do is we will try to analyze our transmission lines with the help of equations. So, what we have to do is we have to derive the equations first. What I take is a small part of the transmission line and the equivalent circuit of the transmission line. I will go for analysis of the transmission line, how the voltage will be transmitted, how the current will be transmitted, and what are the equations of that one. So, for that what I do is I will take the convenient equivalent circuit of our transmission line, that is like L shape. Just observe what I am taking. Let us consider the basic structure of our transmission line, which is the equivalent structure that what I have drawn in terms of RLGC for a differential length delta Z. Let us take the differential length of this transmission line is some delta Z. That for this differential length I am taking these distributed elements, but for the analysis clearly remember these distributed elements are not sufficient, they are not at all useful. For that what we have to do is we have to convert them into the lumped elements. For that just what you have to do is you have to multiply this one with its length. That resistance multiplied with its length will give you the lumped element. Just you observe the units. This is ohm per meter multiplied with meter, ohms. So, this is a clear resistance that what we have. Similarly, if you multiply this one with its differential length, you will get the lumped element here. So, G multiplied with delta Z, what you get is a lumped element. C multiplied with delta Z, what you get is a lumped element. These lumped elements are useful for our circuit theory. Distributed elements are not at all useful. Clearly remember that point. Now, what I am doing is just I am replacing the entire transmission line that what I took with length delta Z with this simple distributed, these are not distributed lumped elements, right. Let us take here at the input I am applying a voltage of V of Z comma T, that at some location Z I am applying a voltage V of Z comma T. Let us take the current which is flowing through this branch is I of Z comma T, that is at the initial current, that is what I am taking is I of Z comma T, and let us take the outcoming current yet Z plus delta Z. If this location is Z, after length delta Z, this length is Z plus delta Z. Let us take the output voltage that what I am observing is V of Z plus delta Z comma T, and the output current that what I am observing here is I of Z plus delta Z comma T. Let us take this branch current is delta I. That what I am doing is I am trying to take all the parameters which are involved in this circuit. That this is the resistance, inductance, capacitance, conductance, and the input applied potential is V of Z comma T, output observed potential is V of Z plus delta Z comma T. This is observed at Z plus delta Z distance. Current is I of Z plus delta Z comma T. Here the applied current is I of Z comma T. In this branch let us take the current is delta I. After that is a very simple analysis, just observation of all these things by using our KVL and KCL. That what you have to do is you have to use the Kirchhoff's voltage law and current law. Now, let us consider the outer loop. For this outer loop, apply KVL. Just observe what I am doing is applying KVL to the outer loop. Don't take the inner loop, just don't take this loop or this loop. For the outer loop, apply KVL. Now, start from here. So, what is the voltage? V of Z comma T minus voltage drop across this resistance is R delta Z multiplied with the current which is flowing through this one is I of Z comma T minus, here what you have is an inductance component, inductor component. That is why the voltage drop across this one is L delta Z d by dt of the current flowing through this one is I of Z comma T. That V of z comma t, initial voltage, in the input voltage, minus voltage drop across this one, minus voltage drop across this one, minus the voltage drop across the output is minus V of z plus delta z comma t. So over. So we took the entire outer loop. For that one, just we applied the KVL. Now rearrangement of this equation is the remaining part. Just take this V of z comma t and minus V of z plus delta z comma t and put the remaining all parameters to the right hand side. That what I am doing is, just observe what I am doing. I am writing like this, minus V of z plus delta z comma t minus V of z comma t. This I am keeping in the left hand side. So this term and this term are left for us, and the remaining two terms will be go to the right hand side. Then what we have here, r delta z I of z comma t plus L delta z d by dt of I of z comma t. These are the parameters that what we have on the right hand side, right? A very simple one. Next, bring this delta z to the left hand side. Here right hand side we have delta z, bring that one to the left hand side. Then it is minus V of z plus delta z comma t minus V of z comma t divided by delta z. So on both sides I am just dividing that one with the delta z, which is equals to r I of z comma t plus L d by dt of I of z comma t. Just simply observe what is the equation that I wrote. That with simple arrangement or rearrangement of these parameters, I got this expression. Now go to your mathematics foundations, that whenever you have this form V of z plus delta z comma t minus V of z comma t divided by delta z, if you apply delta z tends to 0, this may becomes the differential form of this particular function. That f of x plus delta x minus f of x divided by delta x, as delta x tends to 0, just correlate with that one. Then what I am doing is, I am applying delta z tends to 0 on both sides. To get that particular form, apply delta z tends to 0 on both sides. Just I am writing here delta z tends to 0. Here on the right hand side there is no delta z term. So even though you are applying delta z tends to 0, there is no change in this right hand side term. Now observe the entire left hand side term. The left hand side term is nothing but the differential form of this particular function. So clearly write down that one as the differential form of the left hand side function with a negative sign in front of this one, minus d by dz of V of z comma t. That the entire left hand side term is just a differential form of this V of z comma t with respect to z, which is equals to r I of z comma t plus the next term is L d by dt of I of z comma t. But the task is not over. What we have to do is, we have to go for a simple modification again. Just recollect the concepts in our wave propagation, that we converted the dou by dou t operator or d by dt operator into the frequency domain with the help of simple analysis. So, and if you from that just recollect it, that dou by dou t or d by dt operator can be always replaced with j omega. Now what I am doing is, I am using that particular result here. So what is the modification in this one? Minus d by dz of V of z comma t is equals to r I of z comma t plus L, instead of d by dt I can write j omega. So I am writing this one as j omega L I of z comma t, right. So just rearrange this equation, that is minus d by dz of V of z comma t is equals to r plus j omega L I of z comma t. This is a basic equation. Don't think that this is the equation that what we require. This is an intermediate equation which is useful for obtaining the wave equations. What we have to do is, just we need to take the transmission line structure, apply KVL to the outer loop, then go for a simple analysis, that a simple mathematical manipulation will give us this equation. Similarly, what I do is, I will try to relate V and I in another way. That what I do is, I will apply KCL now. So if I apply KCL, so how it will be related once again, that what I do in the next step. So here what I do is, as a next step I will apply KCL at the important node. So let us take this is node A. At this node A, I will apply KCL. It is a very simple one, that incoming current is equals to the outgoing current. So, what is the incoming current here? Applying KCL, just observe that the incoming current is I of z comma t at that particular node. Outgoing currents are two currents are there, which is I of z plus delta z comma t plus another current is flowing through this branch. Just take that one as delta I. Now rearrange this equation again. What I do is I will bring this term to the left hand side. So which is minus I of z plus delta z comma t minus I of z comma t, which is equals to delta I. So once again we are getting a similar form. This may be a differential form of the current equation. If you get an exact equation for this delta I, we can observe that one. So what I do is I will try to get the equation of this delta I. This delta I is again a combination of the current which is flowing through the Z and the current which is flowing through the C. So what I do is I will try to get this delta I. Just directly I am writing, this is a simple circuit theory that you know already. The conductance multiplied with the potential across this one. The voltage across this one is V of Z plus delta Z comma T. Multiplied with the conductance always gives the current. So which is equals to G delta Z, the potential is V Z plus delta Z comma T. So this current is meant for the current which is flowing in this particular branch. Now we have one more current that is flowing through the capacitance, that will be added to this, plus the current which is flowing through the capacitor is equals to C delta Z d by dt of the potential across this one. The voltage across this one is V of Z plus delta Z comma T. That this entire equation, the entire term is equals to the current which is flowing through this particular term, which is equals to the left hand side term. Now what I do is I will go for the same analysis. Bring this delta Z to the left hand side. That this becomes minus I of Z plus delta Z comma T minus I of Z comma T divided by delta Z. That what I wrote on the left hand side, which is equals to, on the right hand side what we have, G V of Z plus delta Z comma T plus, and the remaining term is C d by dt of V of Z plus delta Z comma T. Now once again similar analysis, apply delta Z tends to 0 on both sides. If you apply delta Z tends to 0 on both sides, this entire term is the differential form of this current, and this term in this delta Z tends to 0, this will become 0, this will become 0, so only V of Z comma T remains for us. Here also V of Z comma T remains for us. So how this equation will be modified? Just observe, minus d by dz of I of Z comma T, that this entire term is the differential form of this particular function, which is equals to Z multiplied with V of Z comma T as delta Z tends to 0. This delta Z tends to 0 will give us V Z comma T, C d by dt of V of Z comma T. That is the term that what we got in our right hand side. Once again go for the similar analysis as our first one, equation 1. Instead of this d by dt, we can write j omega, right? So after replacing that one also, the equation what we get is minus d by dz of I of Z comma T, which is equals to Z. Directly I am writing the equation here. Instead of d by dt, j omega is replaced. So V of Z comma T is common, C left for us, that is G plus j omega C V of Z comma T. That clearly observe the form of equation that what we got. The equation what we got in our earlier case is d by dz of V of Z comma T. Here it is minus d by dz of I of Z comma T. Similar form, voltage and current were swapped. Here it is R plus j omega L. Here it is G plus j omega C. I of Z comma T, V of Z comma T. So what I can say is, using these two equations, take this one as equation 2. So using these two equations, easily we can identify or we can obtain the wave equations. So what I do is I will take these equations as the base equations and I will keep them aside. Now what I do is just once again I will go for the mathematical manipulation and I will try to solve these two equations. Before that, just observe what are the components we have. That is a voltage and current. The voltage is a function of distance as well as time. The current is also a function of distance as well as time. So if we want to solve, we have to take two different variables, z as well as, that is nothing but the distance as well as time. but solving that equation may be a little bit complex. So, what we try to do is we will try to suppress the time domain. So, the suppression of time domain will give us the equation in only distance domain, that is easy for us. So, what I do is I will try to take these two equations as a convenient form. Let us take v of z comma t is equals to some vs of z into cos omega t. That clearly this is a function of distance as well as time, this is also a function of distance as well as time, and if we want we can suppress this time domain, but not in this simple way, just you ignore this cos omega t, not like that. For that some mathematical procedure is there. This equation can be written as real part of vs of z multiplied with e power j omega t. That if you take this one, easily you can observe that e power j omega t gives us cos omega t plus j sin omega t, the imaginary part was just eliminated. So, the equation what we get is vs of z cos omega t. Once again this is a time domain as well as a distance dependent wave equation or the voltage equation, that what we have. Now, if you take like this, then it is very easy to analyze. Now, observe here that what I am doing is now at this stage I can suppress the time domain factor, simply vs of z I can consider. So, just suppress the time domain cos omega t now and take this as vs of z. Then d by dz of v of z comma t is equals to simply dvs of z divided by dz. That here clearly remember, we are not ignoring or we are not eliminating, we are suppressing the time domain, nothing more than that. Like that, similar equation can be written as d by dz of I of z comma t is equals to d is of z by dz. So, what I do is I will try to write down these two equations which are time suppressed once again to get a simplified equation. I am writing these two equations, just observe with the time domain suppression, that is minus d by dz of this v of z comma t can be written as vs of z, which is equals to r plus j omega l, I of z comma t can be written as is of z with time suppression. Similarly, minus d by dz of here it is is of z, which is equals to g plus j omega c vs of z. Clearly identify there is no time domain here, there is no time term. So, the equations what we get may be simple, that easily we can solve these equations by taking some mathematical relation between them. For that what I do is I will take this first equation, let us take this is equation 3, let us take this is equation 4. I will take this equation 4 and I will manipulate that one. I will take this equation 3, I will manipulate that one according to the requirement. Initially consider equation 3. If we consider equation 3 and differentiate it again with respect to z, consider this equation 3 and differentiate this one with respect to z again. That what I am doing. This is d square by dz square of vs of z on the left hand side, that what we have, which is equals to r plus j omega l. Obviously, these are the constant terms that what we have for a constant frequency. R plus j omega l, and the right term is here dis of z divided by dz. So, just to solve these equations, what I am doing is I am differentiating this again. Now, we have clear relation between these three equations. Thus, instead of this dis of z by dz, we can replace this entire term. Write down that which is equals to r plus j omega l multiplied with, instead of this dis of z by dz, a negative sign will be added here, that a negative sign I am adding in front of this term, minus g plus j omega c vs of z. Now, you may get some idea why we are getting this. So, why to do all these things? Just imagine and observe here, we have voltage, here we have voltage. But in the previous equation, current equation is there, voltage equation is there. Here if you consider, current is there, voltage is there. So, you have to solve these two, that is a little bit difficult. That is why what I did is, I eliminated the current from the entire equation, that this is a specific equation for the voltage. Then rearrange this equation, that what we have is d square vs of z by dz square minus, that this negative sign will be cancelled. I am bringing this right hand side term to the left hand side. So, this negative sign will carries here, minus, I will consider this entire term as gamma square. That later I will give you what is this gamma and how to remember this gamma, right, gamma square. So, here it becomes minus gamma square vs of z is equals to 0. just observe this equation. I think you are recollecting the equation what we learnt in our wave propagation. In the wave propagation, a similar type of equation was derived. So, d square E of z divided by dz square minus gamma square E of z is equals to 0. That is the equation that what we have in our wave propagation. Here also a similar type of equation will be obtained. That instead of V, what we are getting is, instead of E, what we are getting is V. Nothing more than that. Similarly, if you go for the analysis of equation 4, what we did is we took equation 3 and differentiated it again. Right? We got this equation. Now, take equation 4, differentiate it again, substitute dVs of z by dz here and solve that equation, and more interestingly, what you get is a similar equation in terms of current. That a similar equation in terms of current can be written as d square Is of z by dz square minus gamma square Is of z is equals to 0. You can verify that. That these two equations are similar in all aspects. These two equations are called as the wave equations or the transmission line equations for voltage and current. That for the voltage, this is the exclusive equation, there is no current term here, and for current, this is the exclusive equation, there is no voltage here. Right? Now, we have to solve these equations. Then you will get the exact and the perfect equation for the voltage and current. Right? These are the transmission line equations. If you get solution for these transmission line equations, you will get exact current equation, how the current will be, exact voltage equation, how the voltage will be in the transmission line. So, this is a very simple step. Next, we are going to get the solutions for these two. Now, what I do is, I will try to get the solution for this equation. That get the solution for this equation, and once again convert this one into the time domain. Already we suppressed our time parameter here, in our previous steps. So, what I do is, I will try to get the solution for this one, and I will introduce once again the time domain equations or the time domain parameters here. Now, clearly observe what is this equation. This equation is a second order differential equation. That we have some standard solutions, do not go for any separable variable method, nothing. It is just you remember the standard solution for this second order differential equation. Already this type of equation we come across in our wave propagation also. So, just recollect those steps and try to write down the solution for this. The solution of Vs of z, directly I am writing. So, V naught plus e power minus gamma z plus V naught minus e power gamma z. If you want, just you substitute here and easily this will be satisfied. Right? This is one of the solutions for our second order differential equation. Now, clearly observe what I am doing. I am getting Vs of z. Now, from this one what I have to do is, I have to get Vs of z comma t. So, how that Vs of z comma t was defined? So, Vs of z comma t is equals to, initially we took Vs of z comma t equals to real part of Vs of z multiplied with e power j omega t. Right? After that one we suppress this j omega t, leave about that one. Now, go to the back step and take the time domain factor and introduce here. Now, replace our Vs of z with V naught plus e power minus gamma z plus V naught minus e power gamma z. So, which is equals to real part of, instead of this one, just I am writing this one V naught plus e power minus gamma z plus V naught minus e power gamma z e power j omega t. Now, we have to observe how to simplify this equation. That already we defined one parameter gamma. How we define the parameter gamma? That gamma is equals to, simply gamma is defined as r plus j omega l multiplied with z plus j omega c, which is under root. That gamma square is equals to r plus j omega l into g plus j omega c. That what we defined. Simply this can be described as the propagation constant. Why it is described as the propagation constant? Observe here. The wave equation solution has e power minus gamma t term. That purely depend upon this gamma only the wave propagation will be defined. That's why it is called as the propagation constant in our transmission lines. Right? So, gamma is equals to under root r plus j omega l into g plus j omega c. Now, once again recollect how this gamma can be written in terms of its attenuation constant and phase constant. Alpha plus j beta, where alpha is called as attenuation constant, which is described in Napier per meter. Beta is the phase constant, so radian per meter. Right? So, here clearly once again this gamma can be written as alpha plus j beta, which is similar to our wave propagation. Later I will give you how to remember this one also and what are the similarities for all those equations. Right? Now, replace our gamma with alpha plus j beta, which is equals to real part of V naught plus, this is e power minus alpha z, that what I am writing directly instead of gamma, multiplied with v power e power minus j beta z, that e power j omega t also I am multiplying. This is the first term that what we have, plus v naught minus e power alpha z multiplied with e power j beta z multiplied with e power j omega t. Directly I am substituting gamma is equals to alpha plus j beta and writing this equation, which is equals to, observe the real term here and here. The imaginary term is j omega t minus beta z sin, that is a sinusoidal term. Here also the imaginary is j sin, that is omega t plus beta z. Cos omega t minus beta z left for us in the imaginary real term, the imaginary will be vanished. Here also that is a cos omega t plus beta z will be remains for us, a simple mathematics. Okay, you put it on paper, easily you can get it, right. The left terms are v naught plus is left for us, this is a clear real term. E power minus alpha z is left for us, this is also clear real term. And in this one only cos term left for us, that is cos omega t minus beta z. This is the equation of our wave for the first part. I will explain what is that first part also later. V naught minus e power alpha z left for us, and here also the cos term will be remains for us, that is omega t plus beta z. Just remember e power j theta is equals to cos theta plus j sin theta, that is what I am writing here, nothing more than that. Now imagine these two, this is the first term that what we have, this is the second term that what we have in this equation. This first term is described as the voltage which is travelling in positive z direction, and this is the voltage which is travelling in negative z direction. So why it is travelling in positive z direction, how it is travelling in negative z direction? Just observe here. If it is travelling in positive z direction, what about this e power minus alpha z term? Since z is positive and here you have a negative term over here, that obviously the entire strength will be reduced, right. This is also, it is travelling in negative z direction, means it is taking reflection. So e power minus once again you will get here, so this strength also reduces, right. So a general phenomena will be like this, whenever a wave is propagating in a normal space or the free space or whatever it may be, it's any medium, that the wave gets some attenuation. So are you getting attenuation when it is travelling in positive z direction? Yes. Here also when it is travelling in negative z direction, we are getting some attenuation, the wave strength will be degraded. That's why always clearly remember, this is just a blunt principle, this is a positive z direction voltage, and this is a voltage which is travelling in negative z direction. And for an infinite line, just a simple point, for an infinite line, what about this equation? Clearly remember, for an infinite line there will be no reflection, since the wave is an infinite, it's always the positive wave will be there, that this entire term will be vanished. Put z is equals to infinite here, so that when it is reflecting, that if you put minus infinity, obviously this term becomes 0, right. So what simply you can understand is, whenever the wave is travelling in any medium, that it have a positive z direction or whatever it may be, positive direction voltage as well as a negative direction voltage. Whenever the wave is or the line what we are considering is infinite, then the wave is or the voltage is travelling in an infinite line, there will be no reflected wave, the reflected wave will be completely vanished. That what we are supposed to remember. Similarly, we have one more equation in terms of current, d square by dz square is of z is equals to, or minus gamma square is of z is equals to 0, that what we have. If you go for the analysis, you will get similar type of equation, that it's I naught plus e power minus alpha z cos omega t minus beta z plus I naught minus e power alpha z cos omega t plus beta z is the equation for current. So these two are two similar equations that what we have for voltage and current in our transmission lines. So meanwhile, so while describing about all these things or discussing about all these things, we gone through one parameter called as gamma. This is our secondary constant, right. One of the secondary constants gamma was defined and it was observed, that if you get or if you have this RLGs and substitute here, obviously you will get, so what is the propagation constant, what is the attenuation constant, and what is the phase constant while solving the problem. Now what I do is just I will give you a simple trick how to remember this. You may not remember the equation for this one, but you remember the equation of gamma in wave propagation. Let us imagine like that. So what is the wave propagation gamma? Gamma is equals to under root of j omega mu sigma plus j omega epsilon. So this is the equation that what we learnt for wave propagation, right. So unfortunately you forgot this and you remember this equation. Then how to obtain this equation? A very clear resemblance is there, just you observe. J omega mu corresponds to inductor, right? L right here, and let us take this R is existing, that you need to remember that point. J omega as it is, J omega, this is R plus, we are writing as the first term. So instead of J omega mu, R plus J omega will comes into the picture. Second one is very easy. What is this sigma? Conductance. So direct write this one as conductance G plus J omega. What is this capacitance? Capacitance corresponds to epsilon, which is nothing but gamma square, right? So gamma square is equals to, or gamma is equals to under root of R plus J omega L into G plus J omega C. So there will be clear comparison between these two. Even if you remember one equation, the other equation is very easy. If you remember this equation, just you ignore this R, and instead of L, write down mu. L corresponds to mu. Instead of G, write down sigma. Instead of C, write down epsilon. So this is a simple trick to remember our gamma, right? This is our first second propagation constant, the secondary propagation constant, that we are going to the secondary propagation constant Z0. And how that Z0 is defined? In our previous sessions, that is in our wave propagation, Z0 is nothing but the, where we define that one as eta, intrinsic impedance. Here it is characteristic impedance, there is no difference, both are same. That how it is defined in our previous case, it is positively traveling electric field to the magnetic field, right? Here also the same type of application analysis is required. What we have to do is, you have to take the positively traveling voltage and divide that one with the positively traveling current, right? So the ratio of positively traveling voltage to the positively traveling current is now simply our characteristic impedance, that will be described with Z0. Now what we do is, just we will try to obtain the secondary constant also, that is the secondary constant is Z0. For that, what I am doing is, I am taking this equation minus dVs of z by dz is equals to R plus j omega L into Is of z. Very simple trick. Substitute the solutions of Vs of z and Is of z here, that already we obtained the solutions for them. Substitute here. Then this is simply d by dz of, instead of Vs of z, what I am writing? V0 plus e power minus gamma z plus V0 minus e power gamma z, that is the solution for this Vs of z. I have substituted here, which is equals to R plus j omega L into, what is the equation of Is of z, which is equals to I0 plus e power minus gamma z plus I0 minus e power gamma z. Just take these two solutions and substitute here. Now d by dz of this entire thing, which is equals to minus V0 plus e power minus gamma z as it is, and the internal derivation is minus gamma left for us. So what I am doing is, I am making this one as plus, right? So gamma plus what I have is minus sign here. So what I do is, I will put negative sign directly here. So minus V0 minus e power gamma z gamma. Just that what we have is a simple derivation of this one, V0 plus e power minus gamma z, internal derivation is minus gamma minus multiplied with plus, plus V0 minus e power gamma z, internal derivation is gamma minus, I am bringing here, this is the minus, exactly right, which is equals to R plus j omega L multiplied with I0 plus e power minus gamma z plus, I am dividing this entire term, that R plus j omega L I0 minus e power gamma z. So this is the equation that what we have. Now a very simple thing, compare e power minus gamma z term on both sides, that on the left hand side you have e power minus gamma z term, on the right hand side also e power minus gamma z term, compare them. Now what you have to do is, just compare e power minus gamma z term on both sides. Now what I am doing, just I am comparing, observe, V0 plus gamma, this is the e power minus gamma z term on the left hand side, which is equals to on the right hand side, this entire term is nothing but the e power minus gamma z term, that is I0 plus multiplied with R plus j omega L. Now how our Z0 is defined? The characteristic impedance of the transmission line Z0 was simply defined as the voltage which is travelling in the transmission line in positive direction to the current which is travelling in the positive direction. V0 plus is the voltage travelling in positive direction, I0 plus is the current which is travelling in positive direction. Therefore simply it is V0 plus by I0 plus. So V0 plus by I0 plus will gives you R plus j omega L divided by gamma. There is nothing difficulty in this one. Z0 is equals to under root, that later we will get that equation. So simply it is R plus j omega L by gamma. Similarly, If you take e power gamma z term and compare e power gamma z term, you will get one more term. Interestingly, what you get is gamma by g plus j omega c. Don't think that they are different, both are same. Just what I do is now I will substitute this gamma here and I will check whether they are same or not. For that, take z naught is equals to r plus j omega l divided by, what is gamma? Under root of, so r plus j omega l multiplied with g plus j omega c, which is equals to, after simplification, what you will get here? Square root of r plus j omega l divided by g plus j omega c. So this is the finalized equation of the characteristic impedance. That for the characteristic impedance of the transmission line, so we are taking a very simple analysis, that the solution we are considering and a little mathematical manipulation will give us the answer. So z naught is equals to, just remember this one, under root of r plus j omega l divided by g plus j omega c. You can solve many problems if j, r, l, g, c and the frequency is given to us, right. So if you take this one also, you will get the same equation, you can check it, no problem. Substitute gamma here, substitute under root g plus j omega c into r plus j omega l, then you will get the same equation here. Now you have one more trick to remember this one. As I said for our gamma, here also you have one more trick. Just recollect the intrinsic impedance of our wave propagation. How the intrinsic impedance of our wave propagation was defined? Eta is equals to under root j omega mu divided by sigma plus j omega epsilon. That what we have in our wave propagation. Now resemble that equation for our transmission lines. In transmission lines, eta can be written as z naught, characteristic impedance of the transmission line, which is equals to, instead of j omega mu, you have to write down j omega l. So clearly put this one as j omega l and a resistance will be added here. That what you are supposed to remember. Divided by, instead of sigma, write down g, conductance plus j omega epsilon. Instead of epsilon, write down the corresponding term capacitance. So z naught is equals to r plus j omega l divided by g plus j omega c is left for us. Eta is equals to under root j omega mu by sigma plus j omega epsilon, that is for wave propagation. So if you prepare as similarities between these things, it is very easy to remember 3 points. Wave equations, they are of similar type, where E and HV you will get the wave equations, similar equations. Here voltage and current, you will get the similar equations. And gamma, propagation constant, there you may have sigma epsilon mu, but here what we have is the RLGC. That characteristic impedance or intrinsic impedance, there you may have epsilon sigma mu, but here what you have is RLGC. So what you do is just you try to prepare a comparison table. So if you have a comparison table, it is very easy to remember all these parameters and it is very easy to solve the equations also. Later, while solving the problems, what we have to do is you may take the combinations of this z naught and gamma. What you have to do is you have to take the z naught and gamma, multiply them, divide them, or you may get some other equations that with those modifications individual parameters of like R, L, G, C may be evaluated. So what we have to do is just remember how to represent a transmission line in terms of electrical parameters. So using our R, L, G, C, how to represent it, how to solve the equations of voltage and current. After solving the equations of voltage and current, how to obtain the secondary constants, that is nothing but our gamma and z naught. So with this one, the basic introduction of our transmission lines will be finished. Later we can go for further concepts like wave propagation and different parameters, phase velocity, group velocity, like that we will discuss different parameters.